रिकॉर्डिंग करना है, पक्का करना है। तो स्टूडेंट्स कहते हैं वॉल्यूम ज़रा कम हो गया है, ठीक है, वॉल्यूम बढ़ा दीजिए। हाँ, और वहाँ से आप मुझे वहीं से पूछिए। हाँ, और इसको ज़रा लगा छुट्टी पे रहेंगे। हाँ सर, मंडे को तो थे। हाँ मंडे थे ना। हाँ ये रिकॉर्डिंग पूछना नहीं, पक्का करना है। हाँ, तुम मंडे को तो नहीं थे ना सर? वो इसमें देखते हो छुट्टी पर जाते तो। अच्छा, तुम पूछना नहीं, करना है। ये ऑन कर दिए? हाँ, ऑन है। ठीक है, वॉल्यूम Rahul, is it clear? You're sure? Okay. So we have mass balance, we have momentum equations, but momentum equation combined with the material relationship for a Newtonian fluid. Ladies and gentlemen, the class has begun. Mass, momentum and the material function or material relationship for a Newtonian fluid will give rise to Navier-Stokes equations as applicable for a very wide range of fluids including air and water. So let's say we are going to look at the incompressible version, then del dot u is 0, maybe I can show an extra step here. This is the mass and momentum equations, which just tells you for the momentum equation is mass times density times acceleration equal to body forces and surface forces. So the material function, also called the constitutive relationship, is that for a Newtonian fluid that we write in index notation, so where we have constructed the strain rate tensor to be so some of you may be familiar with index notation. In that case, this del u is just the partial derivative of ui with xj, and the transpose would be I and j interchanged. So when you use index notation, I and j go from 1, 2 and 3 in 3D, which correspond, those numbers correspond to x, y, z in Cartesian coordinates. So substituting this form of sigma in the momentum equation, we get Navier-Stokes equations. So there was some concern about how the stress strain rate relationship is set up. So we will review it as we go along. Okay, so some simplifications. So the moment somebody says Navier-Stokes equations, immediately the word that follows is simplifications. Why is that? Because Navier-Stokes equations are fairly complex. Why are the Navier-Stokes equations complex? That also we will discuss as we go along. But you may be able to anticipate why it's complex. The same equation holds whether it is flow of water in an ocean or flow of water in a tube, sea water versus fresh water, a lake, ambient air, or a storm or a hurricane, or your engine or your turbine or a pump. The behavior of a fluid particle locally satisfies Navier-Stokes equations. So in other words, you have whether it is a storm in an ocean or a proverbial storm in a teacup. It's the same Navier-Stokes equations. You saw an example of it. We had low flow in a tube, and you remember the video. I'm often referring you to the previous lectures. You have to stay connected. That means before you come to the class, just flip through your notebook. So you warm up to the subject. Remember the videos. Just by increasing the incoming velocity, that die, which was straight, became all oscillatory. Similarly, flow past a cylinder, If the velocity was small, it was going over smoothly over the cylinder. You increase the upstream velocity and it was showing a very disturbed flow pattern beyond the cylinder. So, all these states of flow, even in that simple setting, they are solutions of these Navier-Stokes equations. So, definitely these have to be complicated to embed so many solutions within. So, the entire subject of fluid mechanics can be thought of as simplifications of Navier-Stokes equations as appropriate to the problem at hand. So, one is let us say steady flow. Then you can set the time derivative equal to 0. So, does it help making it steady? Well, it does simplify, but then those fluctuations you saw or the vortices shed by the cylinder, they are all time dependent. So, those phenomena cannot be captured if you work with a steady version of Navier-Stokes equations. You have to work with the full form. But for the time being, let us look at some examples where flow can be treated as steady, not forever, just for the time being. Then we also wrote the body force to arise from equal to rho g, rho g k. Body force to arise from a gravity field, then the body force term and the pressure gradient can be combined into a single pressure gradient in terms of a modified pressure P tilde, which is defined as P plus rho g z, where z is a vertical coordinate pointing upwards. So, the equation then becomes compact. So, if I do not show the body force term, assume that P is P tilde. Okay, so, we do not have to repeat it over and over again. Now, let us look at 2D Cartesian form of the mass balance and momentum equations. Then del dot u equal to 0, this we have seen already, will give rise to ux plus vy equal to 0, where these are x and y coordinates, u and v components of velocity. So, let us look at the Navier-Stokes equations. Left hand side was mass times acceleration, right. It was that means a rho into ax, the x component of acceleration, that was u dot del u. So, for u you can substitute the x component of velocity and evaluate u dot gradient of u, which is u ux plus v u y. This we had done earlier. So, rho u ux plus v u y. So, recall that u dot del u in component form will be u dot del u and u dot del v. Okay, these are the x and y accelerations. What kind of acceleration are they? They are called spatial acceleration. Temporal acceleration is changes in velocity with time. Changes in velocity with position will give rise to spatial acceleration. Sum of the two will be total acceleration. This you recall is the Eulerian form of acceleration, and then you have a Lagrangian form that you associate with fluid particles as they move in the flow field. In Eulerian form, you are evaluating all acceleration terms at a point. The advantage of Eulerian is that it gives you a differential equation in the form that is amenable for analysis. What analysis? This book by Kreyszig, which talks about solving differential equations. Then minus gradient of P will have these two terms. So, I am not going to show the body force term here, plus mu del square u. Del square of vector u will be del square u and del square v, and this del square is the Laplacian. So, here it is u x x plus u y y. Similarly, the x, after the x momentum equation, we write the y momentum equation. So, these are, so what are the assumptions that go into writing these equations? One is it is incompressible, steady, 2D Cartesian form with body force term assimilated into pressure. So, but before writing these equations, we had Newtonian fluid, continuum, but a whole lot of approximations. Okay. So, sometimes people ask, you have made so many approximations, how do you know the answer is going to be meaningful? So, in the engineering context, we do not entirely rely on a mathematical model. We always carry out experimental validation. So, you have to ask, do experiments match theory? It is a continuous process. You can't rely on only models, because models, by the time you arrive at the final version, they carry a whole lot of approximations. So, now Navier-Stokes equations were derived roughly 200 years ago. We are still talking about them, which means they have been validated in various situations. Okay. So, let us say the drag acting on a cylinder, you calculate from these equations and you compare with an experimental value, they match. As you improve the experiment, the match keeps improving. Okay. So, so in our own country, there is the Department of Meteorology, that does weather forecasting. So, there is a building in Delhi called Mausam Bhavan. As the name suggests, it is for weather forecasting. Inside that building is a huge computer. Okay. And still they keep asking for bigger and bigger computers. So, what are the equations they are solving? What are the equations they are solving? Navier-Stokes equations. Okay. And how good is their prediction? Of course, it is fashionable to say it is poor, but it is not poor. It's weather prediction. If you say weather in your native place, Bhopal, just assuming an average student is from Bhopal, because Bhopal is somewhere near the center of the country. So, if you want data of weather in Bhopal, you do weather in Bhopal, and quickly you get the data for a whole week. And that week it's more or less all right. Okay, but beyond a week it becomes a problem. Okay, why? Because through the computer you cannot get analytical solutions. You don't get exact solutions. You get approximate solutions through the computer also. That approximation is good enough for 1 week. Beyond that it fails. Then the computer takes the real data at the end of the week and starts again. So it reinitializes itself. How can it get the data at the end of the week? It's where does it come from? Huh? No, experiment is a generic term. Does it come from the wind tunnel? Can the wind tunnel give you weather data over the country? No, it has to come from satellites. So the satellites, which is why the space program becomes so important, that gives you the data to reinitialize the computer program in Mausam Bhavan. And then merrily you do Google search for the weather in Bhopal or Nasik or whatever, and you can see it. You can get the weather of Barcelona if you wish. So I am just trying to emphasize that this is not empty rhetoric. This is a very powerful tool. So we are going through it rather quickly. So, but then you will have to go through it. It's like creating surface finish. You have to do it many times. Then yes, you have a good surface. So what do you do with these equations? You solve them. Solve them for what? Velocity and pressure. What are the unknowns? U, V and P. See, X, Y, rho and mu are fluid properties, they are given to you. Okay. X and Y, these are independent variables. The dependent variables are velocity components and pressure. Okay. How many unknowns? 3. How many equations? 3. So this forms a closed system of equations, and these are differential equations. They will require initial conditions if there is time dependence, and boundary conditions. You understand that differential equations can be solved with initial and boundary conditions. Now we said these equations are geometry independent. So where does geometry come in? If I say I solve for an engine, where does the engine geometry come in? Huh? Where does the engine geometry come in? Through boundary conditions. Okay, the boundary conditions will define the geometry of the problem. If you are doing parallel plates, you apply boundary conditions at the lower wall, top wall. If it's a tube, at the wall and the axis of the tube. So these will define the geometry of the problem. So geometry prescription via boundary conditions. And if you have time dependence, then you have to prescribe initial conditions. You understand, BCs are boundary conditions. IC would be, at least in the mechanics framework, it is initial conditions. So let's say you use tools of analysis. If you go for a computer program, so that would be a in the computer jargon it is called algorithm. You have algorithms for solving Navier-Stokes equations. So when you bring in computers and fluids together, the subject is called computational fluid dynamics. Now, the subject is so important. Now they are developing dedicated computers to solve only flow equations. And these computers have a very symbolic name. They are called Navier-Stokes engines. That engine is a computer, okay, which is solving these equations using algorithms. So are we going to study those algorithms? Sadly, no. But Navier-Stokes I have introduced to the class, and it's there in the book also. Now the term computational fluid dynamics was not there in the earlier versions of Frank White. In the new versions he is talking about it. So when you solve for u, v and p, its flow past a cylinder, you give me velocity distribution. These are all distributions. And then a person may say, so what? Ultimately we want forces. Okay. Of course, force and energy, these are the twin objectives of the subject. And by energy we mean energy expended. So how will you find forces from u, v and p? And what are the forces? Of course, you may want to have a force distribution in the flow field, but usually it is force acting on an object, a solid object. So how will you find forces? From stresses, right? So we have the constitutive relationships that have gone into the governing equations have to be recalled to give you the stress distribution. So UVP will give you sigma, which will give you forces and moments and energy expended. So all those are beyond forces, moments. In our previous discussion, and this we had used the word loss. Energy loss is the energy to be expended by an external device. So earlier we wrote sigma ij equal to minus p delta ij plus 2 mu epsilon dot ij. So velocity will go into the strain rate and pressure goes in here. Together it will give you sigma. Okay. So now you have obtained answers in Cartesian coordinates. So these equations, the constitutive relationship also has to be expressed in Cartesian form. So you may want to write I equal to 1, j equal to 1, or you may write I equal to x, y, z. Now we are working in 2D, so x and y, j also x and y. So what are the components of sigma? Sigma xx, sigma yy, sigma xy, which is equal to sigma yx, and this epsilon dot this is epsilon dot. What is P delta ij? It's I'm just writing that term. It's minus P 0 0. That's that term. And sigma ij is sigma xx Okay, so this is a matrix equation. So that means you can equate every entry of the matrix at the corresponding locations. So now I write the constitutive relationship in Cartesian form. Sigma xx is equal to minus p plus 2 mu ux. Sigma yy is equal to minus p plus 2 mu Vy. Sigma xy is equal to sigma yx is equal to mu uy plus Vx, where these partial derivatives indicate differentiation. I mean, these what am I saying? The suffixes indicate partial differentiation. Okay. This is the Cartesian form of the stress strain rate relationship. So, once you solve Navier-Stokes equations, you have u, v and p. Then you substitute ux, so that is a derivative of u with respect to x, multiply by mu and add to p, okay, or I should say add to minus p, okay, that will give you sigma xx. These are the stresses in the flow field. Like the control volume, you get forces acting on the control volume. So, these are stresses acting on a fluid element. So, you have to write let us say for flow over a flat plate. This was a flat plate, and then we had a fluid element near it, and the notation is this is the notation. Okay. So, on the flat plate, if you consider a small element, the forces are sigma yx and sigma yy. Okay, this is the plate. These are the forces acting on the plate. So, sigma yy is minus p plus 2 mu Vy. Okay. So, let us look at these expressions. So, what was sigma yy? It is minus p plus 2 mu Vy, right. This is what we had in the previous slide. Now, if I evaluate at y equal to 0, how can I simplify it? Recall that ux plus Vy is 0. At the wall, this is the wall, u is equal to 0. That is the no slip condition. The surface is stationary, the fluid sticks to the wall, does not move relative to the wall, and therefore, u is 0 at the wall. So, ux, that is the derivative of u with x on the wall, is also 0, because u is 0 on the wall. Therefore, Vy is also 0 from the mass balance equation. So, here you write u0, ux equal to 0, therefore, Vy equal to 0, and sigma yy is equal to minus p. What about sigma yx? This was mu uy plus Vx. Now, at the wall, there is no flow being sent into the fluid. It is the term used is it is an impermeable wall, like this solid surface. There is flow over the surface, there is no flow going in to the flow into the medium from beneath the wall. So, V is 0 everywhere. So, on the wall u is 0, V is also 0, okay, which means Vx is 0. Vx is the derivative of V with x. So, at y equal to 0, sigma yx is mu times the derivative of the x component of velocity in the y direction. Okay. Now, this quantity we had used a special symbol called tau wall, called wall shear stress. and this term is wall pressure. Pressure evaluated at the wall is wall pressure. So, if you want to find the total force acting on the surface because of the stress distribution, this will have to be integrated, right? Force locally, force times the stress times area is local force. You may write dF equal to stress times the local area, and then you integrate over the surface, okay, in the appropriate direction. So, here if you integrate in the x direction, you will get the force acting on the surface, entire surface. So, I can write, so this is a repeat. I had previously we had discussed the utility of stresses in finding wall properties, but now I am connecting it to Navier-Stokes equations. You solve Navier-Stokes equations, get your velocity, get your pressure, and then use constitutive relationship to find stresses, find wall stresses, integrate stresses on the wall to find the total force. So, capital X will be equal to 0 to L mu dx, right. So, this is sigma yx, and capital Y is equal to 0 to L, and with a sigma yy is minus p, where pressure is evaluated at the wall, okay, with the wall being defined as y equal to 0. Okay. Now, this is the overall approach, but now we will use it in simplified, further simplification. We will simplify it so that some solutions can be obtained, rather than writing an answer in symbolic form like this. So, let us look at some simple problems where we can extract a clear solution. So, let us talk of some examples. And we start with, let us say, since we have done Cartesian coordinates, let us stick to a Cartesian geometry. So, we will do Cartesian geometry, we will do a few examples from a cylindrical geometry. We will also look at exactly one example from spherical coordinates. For reasons I will explain at that point. So, this is flow between parallel plates. This is not a Newton's parallel plate experiment. This is flow between, this is like a tube, but you have parallel plates and you are driving the fluid through this gap. Okay. So, there is a fluid medium here, and this is u equal to some capital U. Let us say the lower wall is y equal to 0, the top wall is y equal to h. Okay. So, you have the mass and momentum equations, which I will rewrite So, in many examples, many situations, this gap is small and the surfaces are large. Okay, so, what happens is the flow coming in is somewhat disturbed, but then settles down. and then the changes happening. This is almost like the example of flow through a tube. Low flow rates, you found that the die just moved straight. It was initially slightly disturbed and then it moved straight. It's also similar to that example of a sphere falling through an oil medium. That reminds me, maybe I should show you some more videos. So you will see that, let's say I put a small spherical object at the top of a water column or an oil column. In oil it becomes even more dramatic. It will accelerate and then attain constant velocity. Okay, so there is no change in its movement, the pattern of movement after some time. So that state of flow, so here the left hand side, this is an edge. So away from the inlet plane, so that means the edge effects have died away. By the way, this is not theory. I am not saying they will always die away. This is an example just to solve the Navier-Stokes equations and see if we can get some answers. Okay, so it's you may think of it as a cooked up example, but this example is there not only in Frank White, in many books, which tells you that the example indeed has relevance. So away from the inlet plane, the velocity distribution in a way becomes invariant to x, and the flow is then said to become fully developed. So whether you look at some point here in the channel or some point later, the velocity distribution is unchanged. What do you expect in this problem? How will the distribution appear? At the walls it is 0, velocities are 0 at the wall, but there is some flow taking place. Therefore, the maximum has to be attained closer to the axis. So you expect something like a parabolic distribution. It will increase and then decrease, and it will have a maximum value along the axis. And that distribution does not change from point to point when you are away from the left plane. Flow in a way has stabilized. So if the flow is fully developed, then there is no change in velocity with x. So these two terms are 0. Okay, so you can quickly see that there is a ux here, there is a vx here, you have uxx here, vxx here. So these terms are all 0. That is one. There is a ux here also, which tells you immediately that vy is 0, but v at y equal to 0 is also 0. Therefore, v is 0 everywhere. So it tells you that if the flow is unchanging in the x direction, tells you that the fluid is not mixing up. The transverse velocity is 0 in this particular example. So now you can drop this v, and this also can be dropped. And then this equation is identically satisfied because you have set ux equal to 0. So the reduced form, the x momentum equation is minus the derivative of p with x plus mu uyy equal to 0. And in the y momentum equation, every term is 0 except the pressure gradient. So, this is the reduced form of the governing equations, okay, which need to be solved subject to boundary conditions. The boundary conditions will be y equal to 0 and h, u equal to 0. Okay, so you can see that the system of equations obtained on the right hand side at the top are substantially simpler than the original Navier-Stokes. They apply under very special circumstances of fully developed flow in the gap between parallel plates. So, we will solve this equation next time, but look at another example. If I have the time. Yeah. So, this is flow. So, these examples are also supposed to introduce you to the tutorial problems of tomorrow. So, this is an inclined surface at some angle alpha, and there is a liquid film. So, this is the liquid film or a liquid layer. This is gravity. Now, you can set up the x and y coordinate systems along the incline and normal to it, and this is the z direction. So, there is a liquid layer flowing down an incline. Of course, if the liquid layer were to have a larger depth, the flow pattern becomes complicated. There was an example given in your exam where a liquid layer suddenly jumps and becomes, it's a hydraulic jump problem. So, that's a, there are more complications that will arise. Can those details be predicted by Navier-Stokes equations? Yes. Can you predict both laminar flow and turbulent flow? You have two regimes in Moody's diagram. Can both be predicted by Navier-Stokes? Yes. Okay. So, but then you have to work with the appropriate form, the full form. Don't say flow is fully developed. If it is fully developed, it cannot form a jump. It cannot have any change in the flow direction. Okay, if you say it is steady, then it cannot become turbulent. So, these are consequences of your approximations. Okay, if you don't approximate, then the Navier-Stokes equations will contain all the information intact. So, the best case scenario is solve the full equations. But as we keep moving forward, you will realize that there are difficulties. The equation is not easy to solve. So, I may even tell you in a sort of a grandiose manner that the equation has not been solved. The full equation has not been solved. Only special forms have been solved. Okay, so this is a liquid layer. Let's assume, so if the flow is developing, what will happen to the layer thickness upstream? Will it be thicker or thinner? What do you think? Upstream, will it be a thicker layer or thicker? Why? Because velocity there is connected to some reservoir, let us say, where velocity is 0. Okay. So, velocity slowly keeps increasing, it is like that ball moving down, slowly velocity keeps increasing. So, when velocity is smaller, layer thickness is greater, and then finally it becomes the thinnest where velocity is a constant. When velocity is constant, layer thickness is also constant. So, we are analyzing that part of the flow after the layer thickness has become constant. So, If flow is fully developed, suppose I straight away write V equal to 0, because flow is, this is a, we are going to study after flow has become fully developed, layer thickness delta is also constant. What does it mean constant? Independent of x. So, if flow is fully developed, the transverse velocity is 0. There is only one momentum equation that we can write as in the parallel plate problem as 0 equal to minus d, the pressure gradient, now why is the layer moving down? Because of gravity. So, here is an example where you cannot neglect gravity. In that flow between parallel plates, it was being driven by a pressure difference, a pump was driving the flow, let us say. So, this P should be interpreted here as P tilde, where P tilde is equal to P plus rho g z, which is in terms of x and y, P minus rho g x sin alpha. Okay. So, what about the y component momentum equation? It just tells you that the derivative of P tilde with y is 0. So, this y is in this direction across the layer thickness. Layer thickness is taken to be small. So, there is this is a hydrostatic equation. So, across this layer, pressure variation is very small, it is a small thickness, but outside it is atmospheric. That means, inside it is practically atmospheric. So, in this problem, the pressure itself is atmospheric everywhere in the liquid layer, and flow is driven entirely by gravity. If pressure is atmospheric, this pressure derivative, the derivative of P is also 0, because why? Because P so, it is this term rho g x sin alpha that drives the flow. Okay. So, we will and then this equation subject to boundary conditions. So, we will continue on Friday. We will have a quick review of the stress strain rate relationship and talk about solutions of simple problems using Navier-Stokes equation.